Now in this final screencast on NP completeness, we will look at a catalog of NP complete problems and very briefly sketch out how they are proven to be NP complete. So we have shown circuit sat to be NP complete, and what that means is for any problem in the set NP, say we have all these problems, they can be reduced to circuit sat. So we can solve any of the problems in NP by converting them into an instance of circuit sat and solving that. Now, to show other problems are in NP, we're going to use transitivity. So if we can choose some problem, say we got a new problem here, like SAT or 3CNF SAT or so on, and we want to show it's NP complete, we have to pick some other problem that's NP complete, like circuit sat, and reduce it to our new problem. And that direction of reduction is important because of transitivity. If the arrows are all going the same direction here, then you get transitivity. It would not help to reduce our new problem to circuit sat, because if the arrow went this way, we don't get transitivity to the other problems. So let's take a look here. The general procedure then, again, is we prove that our new problem is an NP, that one can check solutions in polynomial time, and then we prove that it's NP hard, which is what I was just discussing. We will select some known language that's in NP complete, L prime, such as circuit sat. That plays the role of L prime. This plays the role of L. We'll describe some algorithm that will map every instance of L prime to some instance of L. And that's why the arrow is going this way. The reduction is every instance of L prime, the known NP complete problem, can reduce to a carefully constructed instance of our new problem. And having done so, we show that a solution to our new problem implies that it's a solution to the problem that we're reducing to it. And of course, we have to show that all of this can be done in polynomial time, because if it was an exponential time construction, that wouldn't help us with the question of whether we can solve the other problems in NP in polynomial time. So now let's go on to look at some of these problems. The first problem that we're going to add to our set of NP complete problems is satisfiability. This is where we have some Boolean formula phi, which consists of Boolean variables. They take on true or false, and the usual connectives, and, or, not, implies, double implies, and also there'll be parentheses organizing these expressions. So a truth assignment is a set of values for the variables, for these n variables, giving them either true or false. And a satisfying truth assignment is one that, of course, the whole expression evaluates to true. So the problem sat is the problem of determining whether a formula phi is satisfiable, whether there exists a Boolean assignment of values to variables that satisfies the problem. We show that sat is NP complete in the usual two-part procedure. First, we show that it's NP, and that's because clearly, given any assignment of Boolean values to variables in polynomial time, we can plug them into the expression and see if it evaluates to be true. And then also by showing that sat is NP hard, and we do that by showing that all other problems in NP reduce to sat, and we do that by using transitivity, choosing an existing problem in NP complete, and the only one we have so far is circuit sat. So we're going to reduce circuit sat to sat in polynomial time to a simple construction. Just define a variable for each of the wires and then write a formula that is expresses the logic of the circuit. So here's an example circuit, and so our formula will have the output variable x plus an expression for each of the gates. So for example, this logic gate here, which is an AND, has inputs 8, 9, and 7. And so that's expressed by this expression here. X10 will be true exactly when X7 and 8 and 9 are true, because that's an AND gate. In contrast, here's an OR gate. X9 has 6 and 7 as inputs, so X9 is true exactly when X6 or X7 is true. And you can see other ones with the negations involved and so on. So clearly this transformation can be done in polynomial time. Given a description of the circuit, we can translate the gates themselves into these Boolean expressions. Of course, this is proven formally in the research literature, but clearly if this has a satisfying assignment of Boolean values to the variables, the circuit will also be satisfiable. So we have used circuit SAT to show that SAT is NP complete. Let's now go on to something called 3 conjunctive normal form satisfiability. 3 conjunctive normal form, what we're going to call a 3CNF, is a restricted version of a Boolean formula. And why might we want to do that? Well, when we do reduction proofs, when we try to show that other problems are NP complete, we have to show that we can handle the full complexity of the problem that we're reducing to our new problem. And the full complexity of Boolean formulas makes that really hard. So if we can show that a simpler version of a Boolean problem is also NP complete, then that gives us a simpler reduction proofs in the future. So here's a restricted form of Boolean formulas where conjunctive normal form is a conjunction of clauses, a clause and a clause and a clause. And 3CNF is when each clause consists of exactly 3 literals. A literal is either a Boolean variable or its negation. And 3CNF, these are disjuncts. So it's always a conjunction of 3 disjuncts. It has a very standard pattern, and we're going to see that that's useful later on. So 3CNF is a lot like SAT. We're going to ask, given an arbitrary formula in 3CNF form, is it satisfiable by an assignment of truth values to the variables? That 3CNF SAT is in NP is easy to see, that you can just assign truth values to the variables and check whether the whole expression is true in polynomial time. The reduction will be of SAT to 3CNF, and through a process here that I will give an example of in a minute that'll make it clearer. But we're just going to parse the SAT expression into a binary tree, and then we're going to introduce variables for the internal nodes. And since a binary tree has form, node to child, and each node has a variable related to it, we're going to be able to write a triple that relates the variable here to the variable here and the variable here. And so we're going to produce from that an equivalent expression, and then we're going to use De Morgan's laws and other laws to convert it to first to CNF and then to 3CNF, where sometimes we have to throw in some dummy variables to meet the requirement that every clause have 3 disjuncts. So here's the example. To save time, we won't work it out in detail, but suppose we have this arbitrary instance of a problem of SAT. We want to show that we can reduce it to 3CNF SAT. So given your arbitrary expression from SAT, you parse it and you produce a binary tree like this. The main conjunct here is and, not x2, everything else. So there's a not x2, here's the everything else in this subtree here. And then you go on. You assign, you give variable names to each of these nodes. So essentially you're given each of these expressions gets their own variable name. Parse that out. That's an OR of x1 implies x2. So here's the x1 implies x2, and not, which is here, of all this other stuff, which is down here. So then once you parsed out the tree, then you can write the tree out as another expression that's logically equivalent, but now it has all these extra variables in it. And then you do various conversions, because we can't have variables by themselves. We're going to have to throw in dummy variables to make that into a triplet. We're going to have to get rid of implies and double implies, and convert everything into 3CNF using De Morgan's laws, for example, and the truth tables for the definition of implications and double implication. Eventually turn it into an expression that looks like this, a conjunct of disjuncts that has the same logical conditions. So you can read the details of that transformation in the text, but it shows that the result will be satisfied if and only if the original formula is satisfied. So SAT can be reduced to 3CNF SAT, which means that you can solve everything in NP using 3CNF SAT, because you can use it to solve SAT, which can be used to solve circuit SAT, which we've already shown can be used to solve everything. So we've just done this, and we're now going to take a branch down into graph problems. All of these are graph theory problems. And then at the end of the screencast, we'll go back and we'll just do one example of a numeric problem, also using 3CNF SAT. Okay, now in the world of graph theory, a clique is a subgraph of a graph where every vertex in the subgraph is connected to each other. And here's a bunch of examples: a 2-clique, 3-clique, 4-clique, and so on. The clique problem is the problem of finding a clique of maximum size in a graph. And this has many applications in various domains. We can turn this optimization problem, finding the maximum, to a decision problem asking, does the graph have a clique of size k? So that's what the problem clique is. So it is easy to check that a solution to clique in polynomial time, giving a certificate that consists of the proposed vertices. You just check that they're all connected to each other. The reduction now, we're going to reduce 3CNF SAT to clique, and here's where we use the logically restricted form of 3CNF SAT. This would be a lot harder to do with satisfiability. So for each of the conjuncts in a 3CNF SAT problem, each conjunct consists of a disjunct of 3 literals. We're going to make a triple of vertices corresponding to this triple of literals. So here we have, for example, x1 or not x2 or not x3, and they each get a vertex, x1, not x2, not x3. And so there'll be triples corresponding to every clause here. And then we're going to draw, we're going to put edges between vertices, only between vertices to other clauses. There's never edges in between the vertices within a clause. And the edges will only be there if a consistent assignment is possible. For example, we can assign to x1 and x2 any Boolean values, and there won't be any conflict between them. So we have this line right here. Whereas on the other hand, x1 and not x1 can never receive the same assignment. They'll never be consistent with each other, so we do not have a line there. So finally, we just ask whether this graph has a k-clique, where k is the number of clauses. And so if it does, if you can pick 3 nodes in here, this means that it is possible to give these 3 variables Boolean values that satisfy all 3 of these clauses. So you can find a k-clique if and only if there's a satisfying assignment, because the fact that it's a k-clique means all of them are connected to each other. That means that they're all consistent with each other, because the line means that they're consistent. And also, because it's of size k, you're covering the k clauses, so every clause has a literal that is satisfied, so the overall conjunct is satisfied. Now let's look at the problem of vertex cover. If you have a graph, a vertex cover is a set of vertices that touches all of the edges. Basically, vertex covers an edge that it's incident on, and you want to find the set of vertices that cover or touch all the edges in the graph. Now, the optimization version of this is to find a vertex cover of minimum size. What's the smallest number of vertices you can pick and still touch all the edges? The decision problem, of course, is to say, here's a graph, is there a vertex cover of size k? This reduction is rather clever. Well, first of all, let's say vertex cover is an MP, because given a graph and a proposed set of vertices, we can just look at each vertex, check off the edge it covers, and then make sure all the edges are checked off. So it's an MP, and it's MP hard because we can reduce the clique problem to vertex cover. If this is the clique graph, we construct a vertex cover instance by taking the complement of the clique graph. All the edges in the VC instance are exactly the opposite edges that are not in clique, and vice versa. And then we're going to claim that this graph here, which is actually what we're calling G, has a clique of size k if the complement graph, which I'm calling GC, has a vertex cover of V minus k. Now let's look at why. Well, first of all, we know that if there's a clique in this graph here, then all of these vertices have edges between all of them, and so none of them have edges between them here. So we don't need to include them in the vertex cover on the right-hand side, because for any edge in the graph on the right-hand side, it will always involve at least one vertex that's not in the clique. Because if both of the vertices were in the clique, that edge wouldn't be there, because this is the complement graph. All the edges in here are not in here. So that way we know that we can make a vertex cover of size d minus k. Now notice that there's no claim that this is a minimal vertex cover. It's just saying it is a vertex cover. There may be other cliques in there as well. Now, reasoning in the other direction here, the k edges not involved in the vertex cover here cannot have any edges between them. Because if they did, like that, then you would have to pick one of them to cover that edge. Because they're not in the vertex cover, they don't have such an edge between them. And not having any edge between them, a set of vertices that don't have any edges between them in this graph, all have edges between them in this graph. And so that means that they must be this vertex cover here. Hamiltonian cycle is the problem of showing that a graph has a cycle that visits all the vertices of the graph. We can check a solution in polynomial time just by being given a certificate, which is a sequence of vertices, and checking that you never visit any vertex twice. All the vertices are visited, and you end up back at the same place. The MP hard part is reduction of vertex cover to Hamiltonian cycle. So given an instance of vertex cover, for each edge in the graph for vertex cover, we're going to make one of these widgets. And this is a really clever, complex reduction. So one of these widgets for each edge going between U and V. And so you can see U and V are labeling all of these vertices here. And the widget is constructed such that there are three ways to get through to make a Hamiltonian cycle that visits all the vertices in the subgraph here. One is if you enter with UV and run through the whole vertices and exit UV, you're getting all of the vertices in there. And this corresponds to using vertex U in the cover. If we choose instead vertex V in the cover, we're going to enter on this side, run through all the edges, and exit on that side. If both U and V are in the cover, then we'll run through the widget this way. We then chain together all these widgets and sequences so that all the widgets for a given vertex, say U, are chained together. And then finally, we will add selective vertices. That's these vertices here, which correspond to selecting a vertex that's going to be in the vertex cover. So this is an example for this particular graph, which is only 4 vertices. And then the vertex cover will be found in the Hamiltonian graph by finding a path that, say, starts with S1. We've selected this vertex. There's W is the one being used. Run through W's widget, and then go over here, continuing with another widget for W, and go over here. Here's W again, running through this widget. And then we use the selector S2 to go through Y's widgets. Run through there, and here we go again. Y, run through there, and then we get back to where we started. So that Hamiltonian circuit corresponds to selecting this vertex cover. Pretty clever. Finally, our last graph MP complete problem is the famous traveling salesperson problem. And this is where you want to visit n cities, each city exactly once. You are doing a Hamiltonian cycle, which gives us a big clue to what the reduction will be. But we want to make a tour of minimum cost, so there's distances between cities. We're going to assume a complete graph. We can go directly between any pair of cities, but at some cost. The optimization version of the problem is to find the tour of lowest cost. The decision version of the problem is to find a tour of the cost at most k. So the only known solutions, brute force, is n factorial, really, really slow. There are dynamic programming algorithms that do it in n squared 2 to the n, which is actually pretty bad as well. And so the joke here is it might be easier just to not travel at all and sell on eBay. This is an MP, of course, because given a tour, we can just run through the tour and check that it has cost at most k. But we're going to reduce Hamiltonian cycle to traveling salesman problem. Hamiltonian cycle, the graphs need not necessarily have an edge between every vertex. So we'll model that in TSP by saying we're going to give the edge a cost 0 if it is in the Hamiltonian cycle, and a cost 1, i.e. more expensive, if it's not in the Hamiltonian cycle. So now we can ask whether there is a traveling salesman tour with the cost k is equal to 0. So that means it's not using any of the edges that are not in the graph, in the Hamiltonian cycle graph. And so if there is such a tour with cost at most k equals 0, then there must be a Hamiltonian cycle in the original graph. Well, those were the graph MP complete problems. Let's now step back here. We go back to 3CNF SAT, and we're going to use this to do a final numeric MP complete problem. So many MP complete problems are numeric problems, and here's one example. We've already mentioned integer linear programming. Subset sum is you've got a bunch of numbers, you've got a set of numbers, and you ask, does there exist a subset S prime of that set of numbers such that they sum exactly to some value t? Like here's the joke, here's a menu, and the people ordering, some wise-ass computer scientists, are asking the waiter to bring exactly $15.05 worth of appetizers. So of course it's easy to check a subset sum in polynomial time. Your certificate might be the proposed numbers, add them up, make sure they add up to t. The reduction is to reduce 3CNF SAT to subset sum. So let's suppose we have an expression from 3CNF SAT like this, a conjunction of disjuncts, and they have this very clever way of constructing a set of numbers. Each variable up here will have a number here for each variable in its negation, and so this 1 here says that this number here corresponds to this x of 1 here. So we're constructing these numbers as columns of digits. And we're also going to put a 1 in the column for the clause that it's in. So for example, x1 is in clause 1. That's right here. We have not x1 is in clause 2. So here's the not x1, the second variable for x1, and it's in clause 2, as well as clause 3, where is it right here. So we also have 2 numbers for each of the clauses, and these are simply going to be, they're going to be slack variables. They're going to have a 1 or a 2, and so we can throw these numbers in if we need them. And then we're going to ask to come up with a target sum, which is exactly 1, 1, 1 for as many variables as there are, 4, 4, 4, 4 for as many clauses there are. The only way you can choose a subset of these numbers to add up to this number is if you are able to choose numbers that correspond to exactly to each item being given in a Boolean assignment, whether it's the item or its negation. So you'll get a 1 in each column here because you've picked each variable, you've given it either a true or false value. Now for the clause columns, you could have 1, 2, or 3 of the variables. It's possible for all 3 of these to be satisfied. So you could have 3 1s contributed by all the variable numbers here, the numbers corresponding to the variables. And so then you use these slack variables to make up to reach a sum of 4. And of course you can't achieve 4 with the slack variables alone because 1 plus 2 is equal to 3. So you have to get at least 1 from your variable corresponding to a literal getting a satisfied assignment. Well, let's wrap this up by noting that there's a huge number of problems that are MP complete. And so here's some categories of problems for which we know MP complete problems. Besides graph theory, there's problems in network design, which includes some spanning tree and flow problems. There's problems with sets, storage and retrieval, compression, sequencing and scheduling, optimizing certain kinds of scheduling using resources, and mathematics and algebra, even games and puzzles, logic, automata and language theory, computational geometry, and program optimization, and various other problems. So this shows that this is really, you need to be aware of MP completeness because it's fairly likely that you may eventually encounter some problem you want to solve that turns out to be MP complete. So it's good to have a reference. Of course, you can search on the internet, and the Gary and Johnson book has an excellent catalog of problems. So that concludes our review of MP complete problems.